Renaissance during the 15th century, ballet is an ancient form of art with popularity beginning in the countries of France and Russia. Over numerous centuries, while the styles and social dynamics that are central to ballet have grown and evolved, the physics behind ballet remains the same. Ballet dancers utilize two types of shoes, flat shoes and point shoes. The bottom of both types of shoes reduce friction, so it is easier for the dancers to turn. Friction between the toe box of the point shoe and the floor provides the torque for spinning and turning, in addition to the torque provided by the leg of the dancer, which acts like a lever. There are three main parts to these shoes: the toe box, which supports the dancer's toes during elevation, the shank, which provides support to the arches of the dancer's feet, and the ribbons, which secure the shoes to the dancer. What stabilizes the dancer on point is the upward tension in the Achilles tendon as the shoe pushes into the floor. The Achilles tendon must be able to withstand 2 to 3 times the dancer's body weight, meaning a tear in this tendon would mean the end of the dancer's career.
Balance is a result of static equilibrium where the net force is equal to 0 and the sum of torque is 0, and the dancer's center of gravity is vertically aligned with his or her body. Note that because the force and torque are 0, the momentum and angular momentum stays constant.
One type of turn in ballet is called the pirouette. Rotational inertia plays an essential role in this dance move. Rotational inertia equals mass times radius squared. Angular velocity and inertia are inversely related, meaning that when angular velocity decreases, rotational inertia increases, and when angular velocity increases, rotational inertia decreases. Rotational inertia helps determine how difficult it is to start an object, or dancer in this case, spinning. The greater the mass, the greater the inertia.
Dancer jumping is an example of projectile motion. The only force that acts on the dancer in air is its vertical gravitational force, which is proportional to mass. There are no horizontal forces acting on the dancer while she's in air. In a fouette, the dancer starts by turning, with their arms brought in to the center of axis. By keeping the arms close to the body, this is the same as decreasing the radius. Because the rotational inertia is small, there must be an increase in angular velocity. Rotational kinetic energy is equal to 1/2 inertia times the angular velocity squared, where angular velocity or rotational velocity is defined as v over r. The dancer pauses by extending her arms and legs. In doing this, she increases her radius, thus increasing rotational inertia, yielding a smaller angular velocity. Then, the dancer continues turning, with her arms returned back to the center.